All right, so as I said before, full credit to Mr. Dickey, this is his question. Because he teaches Physics 30, he has seen a lot of examples of roundabout questions that ask about simple concepts. Okay? This is a prime example. Right? There's a lot of information, there's context that can be distracting, okay? But in the end, it's asking only about one thing. That one thing that it's asking about is this. Average velocity is total displacement over total time. Okay, actually, it's more about total distance. It's actually about speed. Total distance over total time. That's really all this question is asking about. Okay, but it's context, all this other information in there. It's all distracting, and it's all designed to do that. Okay, that is exactly the kind of thing they do on diploma exams. Okay, we have actually seen on diploma exams where you have to read nearly 2 pages of text to answer one question. Okay, it's crazy. And even as experienced teachers, we're reading through this question and getting lost in the nearly 2 pages of text, okay, about, I think it was black body radiation or Compton effect or something like that. Okay, but it was a lot of text, a lot of reading, and we had to sort through it. Okay, so here's what we want to get from a question like this. It's important to write down everything that seems like it's something you could use to calculate with. All right? So what we've got, okay, is essentially some information about the first part of Taylor Swift's trip. Okay, because according to my son, who is a big Taylor Swift fan, Luke is like a huge Swiftie. Okay, she always sings the song "Midnight at Midnight." I don't know. I guess that's a thing. I don't know. Or play something from her album "Midnight at Midnight." Anyway, that's a thing. Mr. Dickey knew about it too. I don't know because I'm not cool. Okay, but she leaves Tokyo at 12:01 a.m. on February 11th, Tokyo time, because she's got to get back for the Super Bowl in Vegas. Okay, so time zones wise, Tokyo is 17 hours behind. Okay, Vegas is 17 hours behind Tokyo. They have to fly 9,630 kilometers. Okay. So, let me write that down without the big giant marker. Okay, so in part 1, okay, we know that the distance she's got to fly is 9,630 kilometers. Okay, and she's in this Dassault Falcon 900. I guess that's her personal plane, because when you're as unimaginably rich as she is, okay, you can afford your own airplane. Okay, it can move at an average airspeed of 805 kilometers an hour. Okay. All right. What other things do they tell me? Okay. So apparently she can fly directly from wherever she was singing from, because there's no mention of getting to the airport. So we'll just let that one go. Okay, when she arrives in Vegas, Taylor must wait 30 minutes. Okay, so did they just give me another time? That's probably going to be part of my total time, right? Okay, so it seems like there's a couple of times where there's waits and additional times when I read through the question. Okay, so I'm just going to make a column here that's just called time, okay, miscellaneous. All right, I know that one of those times, and I'm just going to call it time 1, is, what did they say, it was 30 minutes? Yeah, 30 minutes to clear customs. Okay, I'm going to put that in hours. Why am I going to put that in hours?
Because everything else is in something that has to do with hours, so kilometers per hour.
Right, all my speeds are in kilometers per hour. So it makes sense that I keep my unit of time as hours. Okay, so half an hour. Okay, so she takes 30 minutes to get through U.S. Customs. Then she is driven from the airport 6.5 kilometers in a car that can go 27 kilometers per hour. All right, I'm going to make that part 2. Probably going to run out of room here. Okay, but 27 kilometers per hour. for 6.5 kilometers. Okay. Assume an additional 45 minutes of time for miscellaneous delays.
Shouldn't the velocity part one be 805?
Was it 805? I just missed. It's 805. I was looking at that decimal 900. Good eye. You're absolutely right. It should be 805. Okay, so we got 805 kilometers per hour, and we got this additional time here of 0.75 hours. Okay, the Super Bowl starts at 3:30 on February 11th. Does Taylor Swift make it to the game on time? Justify your answer by showing your work. Okay, so can I figure out how long this all takes? Because really that's what's important here, right? It's the amount of time it takes her to get from Tokyo at her concert to the Super Bowl in Vegas. Okay, we need to know how long that takes her versus how much time she actually has to do it, right? So, I've got to figure out the time here, okay? That's going to be D over V, okay? So 9,630 kilometers per hour, kilometers over 805 kilometers per hour. All right, so her flight time is 11.96 hours. Okay, so now I know the time for part one. I've got these miscellaneous times here, the delays and customs and all of that. And I also need the time for driving from the airport to the Super Bowl. Okay, so that's going to be, again, D over V. 6.5 divided by 27, so this isn't going to take very long. Okay, just a few minutes. Okay, 0.240 hours. Okay, can I find the total time for Taylor Swift's trip now? Okay, so I've got my 11.96. So I'm going to take my answer there. I'm going to add 11.96. Okay, plus these two miscellaneous times, 0.5 and 0.75. Okay, so there's her total time. Okay, it's going to take her 13.45 hours to get from Tokyo directly to the Super Bowl. Okay, so now what we got to figure out is, did she have enough time? That's how long it's going to take her. Okay, does she have enough time? So, there's 17 time zones between Tokyo and Vegas. Okay, so that means that according to this question, Vegas is how many hours behind Tokyo? They are 17 hours. All right, so when she left Tokyo, okay, at 12:01 a.m. on February 11th, that was actually 17 hours earlier in Vegas. She actually left on February 10th, if you're on Vegas time. Does everyone follow me there? Because the Earth is round and it spins. By the way, the Earth is round. Okay, that little flat Earth thing is cockamamie. Okay, so it's spinning around and around. Okay, and as a result, okay, some places have different time than others. All right, so if she left at 12:01 a.m. on February 11th, okay, then we got to figure out what is 17 hours earlier than that. Okay, so what we're going to do is we're basically going to say in 24-hour time, she left at technically 24:01. Okay, if I subtract 17 from that, I should know what time it was in Vegas when she left. Everyone okay with that? Okay, technically it's like 001, okay, but I'm going to say it's 24:01. Okay, minus 17. Okay, that should give me 7 o'clock in the morning, 7:01 in the morning, yeah? Okay. Okay, so it was 7:01 a.m. Vegas time when she left Tokyo. Okay, now the Super Bowl is at 3:30. Okay, and it's going to take her 11.45 hours. All right, so if I take, 13.45 hours. So if I add that to 7, according to this, it looks like she's going to be a little late. Because 20:45 is what time? 8.
Oh.
Okay, that's about 8:25 or so. Okay, p.m., not a.m.
Wouldn't that be 8:25 on February 10th?
Sorry, you're right. Good catch. I forgot that part. Okay, remember, she left at 7:01 a.m. February 10th in Vegas, because Vegas is behind. Okay, so she's actually going to arrive at the Super Bowl at 8:45 or 8:25. February 10th. Did she just go back in time? She arrived in Vegas before she left Tokyo. Because the earth is round and all that stuff. Okay? So she's very early, not very late. Okay? She's actually arriving there the day before the Super Bowl. Well, that's convenient. She'll have lots of time. Find her tickets and whatever. Is she doing the halftime show?
No.
Is that why this was a big deal? She's just going to the Super Bowl?
People just don't want her at the Super Bowl.
What's that?
People just don't want her at the Super Bowl. So they were kind of hoping she'd be late.
Okay. I don't keep up on these things. All right, that sort of makes sense? Very distracting question. Okay? But really, when it comes down to it, what did we have to do for math? B equals D over T, and then we had to do the whole thing that I screwed up about February 10th. Okay? And adding the time on there. And in the end, it's not a particularly difficult math question, okay? But it is a difficult contextual question. Okay, everybody come up and grab a Chromebook. We're going to look at some of the stuff in that graphing lab there. All right, so what we're going to start today is how we treat vector quantities, and more importantly, how we combine them, how we add them together in various situations. We're going to start out with the simplest ones, okay, and that is collinear vectors. You've already been doing that because you've done problems with north and south and up and down, okay? So you kind of already are familiar with those. You probably just haven't done them in the way we're going to do all vectors from here on out, right? So collinear vectors are ones that are along the same line. We also sometimes call them one-dimensional, okay, because they only go in one plane. Okay, they can go forward and backward, but that's still only one plane. Okay, if it's two-dimensional, then it can go forward and then to the right. Okay, now it's 2 dimensions. Okay, so we kind of follow the difference. So collinear vectors are considered one-dimensional because they only stay in one plane. Okay. All types of vectors are added by placing them tail to head, right? And I kind of showed you this back a couple of days ago when we were doing one of those V equals D over T questions. Okay, but basically it means all vectors are drawn like this. So if this was a 1.5 meter long vector, okay, and I wanted to add it to a 1 meter long vector, okay, I would put the 1 meter long vector on the head of the first vector. Okay, that's tail to head. Okay, so we draw it like someone was telling us a story. First this object did this, and then it did this, and then it did this. And we just keep putting the vectors on the head of the last one. Okay, everybody all right with that? All right, did you also notice that I had a little bit of scale on that diagram? My 1 meter long vector is shorter than my 1.5 meter long vector. Okay, is that important? It is. I don't have to actually measure it out. That takes way too long. Please don't ever do that. Okay, when we're drawing vectors, please don't take out a ruler and actually draw everything to scale. It takes way too long and is completely unnecessary. You just have to make sure it's somewhat to scale so your diagram doesn't lie to you. Okay? All right. We're going to understand that vector quantities also have magnitude and direction. We already know that, okay? And all vector quantities are added the same way. It doesn't matter whether it's a displacement vector like these two, or it's two velocity vectors, or two acceleration vectors, or in the next unit, two force vectors, okay? It doesn't matter what vector quantity we're dealing with, we always draw them tail to head and add them in the same way, okay? All that changes is at the end, if I'm doing displacement, I get a displacement result. Okay, if I'm doing velocity, you get an average velocity result, or an average acceleration result, or an average force, or net force result. Okay, the method is the same. Okay, so when we were talking about vectors the other day, okay, we said that vectors have magnitude and direction. So when I draw them, I have to reflect both of those things. Okay, if I'm told that an object is going 2 kilometers at 30 degrees north of east, I need to draw the arrow 30 degrees north of east, okay, like you see in this drawing here. Now, you do need to know how your compass works, okay, like not an actual physical compass, but like what thing goes at the top, and okay, as you go clockwise around it, it's north, east, south, west, okay, so you got to know that. And all that we do to draw these vectors is basically this. If they tell me my vector is 10 degrees west of south, okay, then what I do is I draw myself a reference line that's due south, and then I go 10 degrees west of that and draw my vector. Now I have a vector that points 10 degrees west of south, okay? So I have a measurement, I have like a reference line, and then I just go from there. Sometimes people like to do this with their hands. Okay, so they're like, okay, it's 30 degrees north of east, and so they're like, okay, I'm pointing east, and now I'm going north of east. That's totally fine, whatever works for you. Okay, some people are visual, some people are kinesthetic. Okay, that's totally fine. You don't have to be ashamed of it. Okay, I had like a couple of kids one time on a final exam that were trying to hide from everyone that they were doing this so that no one would see them. It's totally fine to do that. Okay. So does that kind of follow? Now the length of the arrow represents its magnitude. Okay? Vector quantities have magnitude and direction. So we make sure they're pointing in the right direction by drawing the arrow that way. And the length of the arrow represents how big they are. So a 2 kilometer arrow needs to be twice as long as a 1 kilometer arrow. Okay, pretty straightforward. All right, so the rules, okay, the direction of the arrow gives the direction of the vector, okay, and then on our next slide here, okay, the length of the arrow is proportional to the magnitude of the vector. All right, now, while that seems like a simple thing, it is something you have to do fairly well when we start getting into angled vectors. Okay, especially if you've got things backtracking on themselves a little bit, but not perfectly. Okay, if you don't have at least some representative scale in your diagram, it's possible your diagram will lie to you. Okay, and your diagram will say one thing, and your math will say something else. Okay, here's the problem with that. We all assume that drawing is easy and math is hard. Okay, when in actual fact, most of the time in physics, people have done the math right and the drawing wrong. Okay, but they always believe they're drawing because I can't screw up drawing. Yes, you can. Okay, you're actually less likely to screw up the math. All right. Okay. So if I need to add two vectors, in this case, the simplest ones, collinear. We do what I showed you on the first slide. Okay, I draw the first vector, and then I draw the second vector as though it happened right after the first one. I put the tail of the second vector on the head of the first, always drawn tail to head. Okay, so in this case here, right, we have a 275 meter due east vector followed by a 125 meter due east vector. All right, now we do something a little bit different with our vectors in this class. Rather than labeling like A, B, okay, like they do here, okay, we draw the vector. Come on. Okay, we draw the vector, okay, and then we say 275. We put the value on top of it, okay, and then our next vector here, okay, we actually put the magnitude right on it. Okay? Rather than saying this is line AB, and this is line BC, and this is line AC. We don't do that. Okay? We actually put the numbers Okay, what's the total displacement of that object?
400 meters, right?
Almost right. 400 meters due
Oh, east.
east, right, because this is a compass question. Okay, it's right, like according to how we're looking at it, totally, it looks right there. Okay, so that's another thing that does come up. We do have to make sure that we have the right vector on our answer. It's easy to get lost in a question, okay, and say, oh, well, that's to the left. Well, that left could be west. Okay, we've got to make sure we're following the vectors that we're given. Okay, all right, is that pretty easy? Okay, that's what you've already done. You did that in Science 10. Okay, so what we want to look at now are ones that maybe involve two-dimensional vectors, like this. This one you didn't have to do in Science 10. All right, so now we have to remember that displacement is your straight line change in position. So even though this object goes 275 meters due east, okay, and then goes 125 meters due north, your displacement is the red line. Okay, it's that shortest point between, or shortest route, sorry, between your starting point, initial position, and your ending point, final position. Everybody follow me there? Right, that's how we calculate displacement, right? Final minus initial position. Okay, well, when we're dealing with something like this, okay, we have to find that change in position using geometry. Okay, does this make a right angle triangle? Can trigonometry apply to that? Okay, so this is where trigonometry would come in. And the Greek geek. Who's the Greek geek?
Pythagoras.
Pythagoras studied triangles his whole life. Okay, so we call him the Greek geek. Okay, Pythagoras. Okay, so we'll have to use Pythagorean theorem, and we'll have to use a little bit of trig in order to get our angle here, because displacement is, after all, a vector quantity. Okay, I can't just look at this and go, it's northeast. Okay, well, that's true. How many northeasts are there? 89. 1 degree, 2 degrees, 3 degrees, 4 degrees, right? There's 90 degrees between north and east. Okay? If I say northeast, that is not good enough. Okay? That person has 89 choices for which way to go. They are going to be hopelessly lost. They have a 1 in 90 chance of guessing the right direction. Okay? Those are not good odds. All right? So we have to say specifically, it's this angle. Okay? How many degrees north of east, or east of north? Okay. All right. So first thing we want to do is calculate our resultant. That's the Pythagorean theorem part. Okay? I want to find the hypotenuse. I have the opposite side. I have the adjacent side. Okay? So I would simply find my overall displacement, which is the red line. Okay? I'll find its magnitude simply by going 275 squared plus 125 squared. Okay, and we've been doing this since the 8th grade. It's just Pythagorean theorem. All right, so according to this, the magnitude of the displacement, so how far it is in a straight line from point A to point B, okay, is 302 meters. All right, but that's only the magnitude. Now I need the direction. Since I now know all sides of the triangle, could I use any one of the 3 trig functions? I can use sine, cos, or tan. I know the hypotenuse, the opposite side, the adjacent side. It doesn't really matter. I like using tan because I'm a geek and I have my favorite trig function. Tan's my favorite. Okay, but also I use tan because these sides were given to me. I know they're right. If I messed up anything on the hypotenuse, I'd rather not use that number because it might be wrong. Okay, so I always use the numbers I'm given as best I can. So if I want to find this angle here, I'm going to use the opposite side and the adjacent side, which means I'm going to use tan. Okay, so the tan of theta equals the opposite side over the adjacent side. Since I'm actually looking for theta, I've got to bring tan over. Okay, so that means using inverse tan, so tan to the minus 1, of the opposite side, which for this was 125, divided by the adjacent side, 275. So I go second, tan, and then 125 divided by 275. All right, so that says 24.4 degrees. Okay, can I leave it like that, 24.4 degrees? Or do I need to say from where?
24.4 degrees northeast.
North of east. Okay. How do I know it's north of east and not east of north?
It's closer to east than north.
Closer to east than north, and in addition, it's measured from east. My little angle arc here that I drew inside my triangle is touching due east and going north of that. Okay, that's how I tell whether it's north of east or east of north. If I drew my triangle this way, I'd be east of north. Okay, but in this case, because the angle arc touches east, east is my second direction. I go north of east, or measured from east. Okay, because that angle is in reference to east. I go north from east. Okay, everybody all right with that? That one takes a little while. We got to do a few before that one kind of sinks in. Okay. All right, so that's a perpendicular one. Everyone okay with that? Because they're going to get crazy. Okay. By the end of the week, okay, we're going to be doing ones like this. And you're going to have to find the overall displacement from those two angled vectors. Okay, right now that probably looks really intimidating, and I totally meant for it to be. Okay, but here's the thing. It's actually a lot simpler than the diagram looks. Okay, in a question like this, you would be told that this is, let's say, 10 meters, and this is 25 degrees east of north. Okay, and on this one, you'd be told that this is 17 meters, and this is 60 degrees south of east. If you know one side of a triangle and an angle, can you find the other sides? You can, using trigonometry. Okay? So if I knew this side and this side, would I know how far east the object goes in total? Okay? And if I knew this side and this side, I'd be able to figure out how far north-south the object goes as well, right? Okay. So in the end, my resultant would be this line. This side here would be the sum of this side and this side. Would you agree? Okay, like I go east and then I go east again. Well, this is the total east that I go. Hello? Okay. All right, bye. Ethan, your dad's here to pick you up. All right, and then would the same be true if in this part here, I go north X amount, and then in this part, I go south this X amount? Do I end up going further south than north? If I added those two things together, making one negative and one positive, would it come out to that one? Okay, that's where this gets trig intensive. You got to find all those sides, and you got to find them using trigonometry. Okay, sine and cos, okay, and all of that kind of stuff. Okay, you did tons of this in Math 10. Right? You're just going to be applying it to something, let's say, less theoretical, okay, in physics now. right? So that's where we're headed. We're not there yet, okay, but that's where we're headed, okay, over the next little while. Okay, so that's what we just did, okay, we did all that calculating, right, and we'll leave it at that for today. You do have a quiz tomorrow, okay, it'll post here very shortly, okay, you can check it out tonight, there's a solutions video for it, okay. It'll probably be similar to your last one, some graphing, and some beat, okay. Won't have any of this, won't have any of this.